All right, hello everyone, and welcome to Miss Lasley's Algebra 2 video on your parent function. So we're going to go through and we're going to finish up our notes on parent functions. If you've already done some of this, that's okay. We're just going to go back over it really quick to make sure we're all on the same page. All right, so let's see. Is my mouse working? There it goes. Okay, so if you haven't already done so, we're going to go ahead and we're going to fill in these tables and we're going to sketch our graph for these functions. All right, so our first function here, oh, there we go, now my pen's working. All right, we have f of x equals x, so when x is -5, y is -5. They already have -4 done for us, so then we're just going to go through and fill this in. You can either use your graphing calculator or you can use Desmos, whichever one you have available at the time when you're trying to do this. All right, and then graphing my line, I'm just going to plot those points in both directions, and I can go ahead and connect my dots. Oh, that was a little curvy. That's okay. I did my best. All right, so filling out name of the parent function. This is a linear function. All right, and if you notice, both of the ends of this graph are continuing. They have an arrow, right? We have an arrow here and an arrow here. That means that our line is continuous and it is going to continue in both directions. So our domain is going to be -infinity, less than x, less than +infinity. All right, another way of writing this same thing is that special r, which is our symbol for all real numbers. So all real numbers are going to be in our domain. Now, because we are pointing up and we are pointing down, that does mean we're going to include all of the y values as well. So our range is going to be the same. We're going to have that -infinity to +infinity with y in the middle, and there you go. There really isn't very many special features of this graph. Maybe just a couple things to take note of. We've got our y equals mx plus b, where m is our slope and b is our y-intercept. All right, so that is our linear function. We should all be feeling pretty good about that. All right, scrolling this way, so x squared, this is your squaring function. All right, it's called the quadratic function. We'll fill that in a sec, but let's go ahead and fill in our table. All right, so what we're going to do is just want to square all of our x values, and just remember, when you square a negative, it does become positive, because -4 times -4 is going to be +16. All right, so we've got 16, +9, 1, 0, 4, 16, and 25. Now, all these points are not going to fit on our graph, so we're just going to do our best to get the points to fit that we can. All right, so we've got 0, 0, 2, 4, 9, and then we'll just mirror the points on the other side. 1, 2, and then 1. All right, now the one thing that I do want to say when you are graphing your quadratic functions, this is a curve, all right? It is not a straight V, all right? That is a different graph called the absolute value graph. So we want to make sure that when we're drawing this, we curve it right underneath. So it's going to have a little bit of a curve there, all right? It's not going to be a V, but we want to make sure we know that it kind of curves. Okay, so name of this parent function is the quadratic function. All right, now domain, we do have our graph pointing in both directions. We have the arrows on the end again. So we are going to keep getting wider. I know it looks pretty skinny, but it's going to continue to get wide. The quadratic function just grows taller faster than it grows wider, but that's okay. All right, so we do still have all x values. So our domain is going to be that all real numbers, that -infinity to +infinity. And our range, now this one's going to be a little bit different, because if you notice on our graph, we don't have any y values down below, our little u. That point right there is called our vertex. All right, we don't have any points below that vertex point, so we can't include those y values. Our very first y value is 0, and then it will go up. So for our range, we have 0, and it's less than or equal to, because we do include 0. 0 is on our table, so 0 is included, so we'll use the less than or equal to. Y less than infinity, because it does point up for forever, so it does go to infinity. Special features, they really don't have that many special features. The one thing that I want to take note of is this point right here. That 0, 0 is called our vertex. And it's going to be either the lowest, like it is in this case, or sometimes we might have it flipped upside down, then it would be the highest point. Right, so the vertex is either going to be your lowest point of your graph or your highest point, depending on if it's opening up or if the quadratic opens down. All right, moving on then to our, wrong way, there we go, our x cubed function. So let's go ahead and fill in our table. Now, when you cube a negative, it actually does stay negative. So a cube is saying -4 times -4 times -4. That is a negative times a negative to get a positive, and then a positive times a negative to get us another negative. So with cubing functions, all right, it does stay negative. So -4 cubed is -64. -2 cubed is -8. -1 cubed is -1, 0. And now we have the positive numbers. So we've got 8, 27, 64, and 125. All right, plotting these points, you get the 0, 0, the 1, 1, -1, 1, 2, all the way up to 8, and -2 all the way down to 8. And nothing else will fit on my graph, so now I'm just going to go ahead and connect the dots. All right, so there is my graphed function. This function is called the cubic function. All right, now if you look at our ends to figure out our domain and range, right, we are going to continue to get wider. I know it's growing up faster than it's growing out, but that doesn't mean that we're not going to have all of the x values. We are going to continue in both directions. So our domain is -infinity to infinity, all right, or all real numbers. And our range, because we're pointing up and pointing down, is also all real numbers. So -infinity, y less than infinity. All right, there really isn't any special features for this function. It's pretty much just cubing numbers. We really don't have anything special. In later classes, you will learn a name for this point. It's not a vertex. It's actually something called an inflection point. But we're not really going to use that term in this class. But it does have a name, it does have nice features to it, but it's not something that we need to pay attention to. It's more like upper level, you'll learn about inflection points. All right, next up we have this function right here, which is telling us to take the square root of x. Now, if you put this into your calculator or you put this into Desmos, you will notice that for numbers less than 0, our negative numbers, you're gonna get something that says either error or undefined. That's because you cannot take the square root of a negative number. Because remember, what a square root is doing is it's telling us what two identical numbers multiply to make what we have, right? So the square root of 4 is 2 or -2, right? 2 times 2 is 4, -2 times -2 is also +4. But there's no way to take two identical numbers, multiply them together, and get a negative number. So you cannot take the square root of a negative. It's something called an imaginary number, which we will talk more about this year. All right, so everything that's negative is actually just going to be an undefined or a no value. The graph goes ahead and just puts the dashes, so I'm going to go ahead and do that as well. But then you can plug in anything that's not negative, you can plug it in. So 0, the square root of 0 is 0. The square root of 4 is 2. Square root of 9 is 3. Square root of 25 is 5. All right, so then we can go ahead and graph some of those anyway. So we've got 0, 1, 4, 2, and 9, 1, 2, 3. There we go. All right, and then just connect the dots. All right, this graph, this function is called the square root function. All right, now its domain, is not all real numbers, all right? Its very first x value is right there at 0. So we can't include anything behind 0. So we say that we start at 0, and 0, if you look at our chart, is included. All right, so we're going to do the less than or equal to. So we've got 0 less than or equal to x less than +infinity, because it does continue for all positive x's. Now range, this is going to be a similar concept, right? So if you're looking at our function, our very first y value is right there at 0, right? It doesn't go below 0. There's nothing going on down below the x-axis. It's empty, all right? So our very first y value is 0, and we do get to include it. Again, look at the I boxed that on our table. So we are going to start at 0, and then we're going to continue to grow. It's going to keep growing to get to our positive numbers. So I would say our range is the same as our domain, 0 less than or equal to y less than infinity. All right, good stuff. Special features of this graph. It doesn't really have any special features. The main thing to note is more of algebraically what's happening here. So just a reminder, this graph, you cannot take a square root of a negative number. All right, so can't have negative numbers. Under a square root. Cool. Okay, moving on to the back. All right, so number 5. All right, again, if you haven't filled yours out, definitely go ahead and fill these out. There are some unnecessary dashes in this one, so I'm gonna delete those. Everything in a cube root, which is what this function is called, is possible. There's no undefined or error values that you're going to get. You can cube root a negative number, because remember, if you look at the x cubed function right above this, you do get negatives when you cube negative numbers. So filling in our chart for negative 125, we get negative 5. For negative 64, we get negative 4, negative 3, negative 2, negative 1, 0, 1, 3, 4, 5. All right, and so now I'm going to go ahead and graph that. So we've got 0, 1, and negative 1, and then we have all the way down to 8, negative 2, and 8, positive 2. And so you end up with something that looks like this. All right, so there's our function. This function is called the cube root function. All right, and if you take a look at the ends of our functions, we do go in both directions. For forever, we have those arrows on the end. So our domain, all real numbers, or negative infinity, less than x, less than positive infinity. Our range, now I know it doesn't look like it's getting taller, but it is. It's going to eventually get taller. It's just growing faster than it's growing taller, right? So it's the reverse of like a quadratic or a cubic function, right? So our range does include all our y values. So we are going to have all of those again for this one. All right, so we've got negative infinity, less than y, less than positive infinity. Special features, again, we don't really have anything for that. We do at 0, 0 have another one of those, what's called the reflection or the inflection points like we did for the cubic function, but we don't need to worry about that. And that's not for this class. Okay. Moving on to number 6, all right? So if you don't know what this function is, so we'll do this one. This is called the absolute value function. The absolute value is essentially asking the question, so absolute value, there we go. What is the positive distance from 0? So the absolute value of a negative number is positive. So if you have the absolute value of negative 5, it's asking how far away from 0 is negative 5. Well, it's 5 spaces. So an absolute value function is always going to spit out a positive value. Now that doesn't mean that the answer for absolute value will always necessarily be positive. It just means when you take something out of those absolute value signs, that number will be a positive number always, because when you're doing distances, which you guys would have learned in geometry last year, you only have positive distances. So since absolute value is that distance from 0, it's always going to be positive. So I'm plugging in these numbers. A negative 5 in the absolute value is going to give us positive 5. Negative 3 gives us positive 3. Negative 2 is positive 2. And then our positive numbers stay positive. So it's not like it's flipping the signs. If it's always just spitting out a positive number. All right, so this is an absolute value function, right? And then graphing our points, we have 1, 1, 2, 2, 3, 3, 4, 5. All right, So that's what we have all the way through 5. So then if we just connect our dots, we have this. Oh, that is rough. Let's fix that. It's hard to do the writing back. That was like upside down. Okay, so there's our absolute value graph. So this graph is a V. It is a hard V, right? So we are connecting at one point. There's no curve, all right, which is different from the quadratic function. So your quadratic function has that nice curve, right? At the bottom, we want to make sure that we accentuate that curve so we know that we're talking about a quadratic and not an absolute value. The only functions that have that hard line right there is going to be the absolute value. So please, when you're drawing your own graphs, make sure that you accentuate the curve of your quadratics. Okay, so for domain, we are moving side to side in both directions. So we have all real numbers, or negative infinity to positive infinity. Our range, all right, so just like with the quadratic though, we don't have any negative y values. So we have nothing happening on that negative y-axis. So our very first y value starts right there at 0, and then it will continue to go up. So for our range, we have 0. Now we do include 0. You can always tell because if you look at our table, if 0 is a part of our graph, then we get to include it. It is a part of our graph, so we can say that our range is 0, less than or equal to y, less than or equal to infinity. Special features doesn't really have any, so we're gonna move on from that one. All right, next up. So this graph has a few different names, and we'll get there, but this is your 1 over your x value. All right, so you're going to get a lot of fractions for these ones. All right, so we've got -4 will be -1 over 4. This would be -1/3. This would be -1/2. That would be -1 over 1, which is just -1. Now, at 0, you cannot divide by 0. We talked about this the other day. So this is, you can either put like a slash or you can put undefined, but you're not allowed to divide by 0. So this is not a value that we can have. All right, and then when you plug in 1, you get 1, 1/2, positive 1/3, positive 1/5. All right, so the main thing to pay attention to is right there at 0. All right, now we're definitely going to talk about this function a lot more this year. We do a whole unit on these functions and their special attributes and things like that. All right, this is called your either reciprocal function or your rational function. All right, reciprocal just means flipped upside down. All right, so normally we have like f of x equals x. So reciprocal, we're flipping that x upside down to make it 1 over x. A rational function generally should have an x's on the top and the bottom, but this one kind of counts because it has the same shape. So I either see this referred to as a reciprocal or a rational function. All right, so these graphs look pretty strange. All right, we already talked about we can't have 0 in our denominator, but every other x value is going to be fine. All right, if you graph this one, you would have noticed that it had like a barrier at x equaling 0, and it also has a barrier at y equaling 0. All right, so if you graph these, you get something that looks like, so those are all decimal points, all these other ones. You get something that looks like this. It curves a little bit more. That was a little bit poorly drawn, but the shape is essentially right. So it's got that 1, 1, -1, -1, and then you have just fraction values as you get closer to both of the x and the y axis. These lines that look like invisible barriers, they have a name. These are called asymptotes. A-S-Y-M-P-T-O-T-E, an asymptote. They are essentially invisible barriers that your function will approach but never touch. All right, and they happen in functions like this rational function when we have that dividing by 0 factor, and it happens with our y values as well, because since we have to eliminate the x value of 0, that gets rid of some of the y values. So that way that we will always have some other barrier when you get rid of that x value. All right, so for our domain, we are skipping over 0. So we have to do, we would say, we could say just x cannot equal 0. That will work. We can do that. All right, so all x's. So let's assume that you have all x's except 0. And then for the range, as you can see, it's also not going to cross over the y or the x-axis to give you a y value there. So you also don't have y as 0. So x can be everything except 0, and y is going to be everything except 0. All right, special features. We have 2 asymptotes. We have a vertical asymptote, which is the line x equals 0. Asymptotes are lines, so it's an invisible line at x equals 0. There's a little bit of a lag. It was doing pretty good. All right, we also have the horizontal asymptote. That's the horizontal line that we don't cross at y equals 0. So there's a horizontal asymptote at y equals 0. Oh, just told me I got a low battery. So let's get that. All right, we're plugged in. Okay, and now it's starting, the writing is starting to work. Okay, so we have a vertical asymptote, that's your up and down one. That is the line x equals 0, so that's a vertical. And then we also have one at that horizontal line, y equals 0. Right, that's that line right there. All right, so those are just invisible lines that our graph is going to approach but never cross. Those are your asymptotes. All right, last but not least, you have 2 to the power of x. So x is now our exponent. So 2 to the power of -4 is going to be 1 over 16. All right, 2 to the power of 3 is 1 over 8. All right, 2 to the power, we already got that one, so then this would be 1/2. Now, if you're wondering why we have fractions when we're raising this to a negative, if you do 2 to the power of -2, all right, you should have learned your exponent properties in Algebra 1, but a negative exponent is what we call the reciprocal. So it's going to flip our number upside down. So this is actually the same as 1 over 2 to the power of +2, which is 1/4. All right, so a negative exponent doesn't mean that your number is negative. It means that you have a reciprocal. It means you have to flip it upside down in order to make that exponent positive. All right, and then the rest of them are pretty easy. So 2 to the power of 0, and this is a fun property. Anything to the power of 0 is actually just 1. So 2 to the power of 0 is 1. 100 to the power of 0 is 1. Any number to the power of 0 is just 1. All right, and then filling the rest out, we have 2 to the power of 2, that's 4. 2 to the power of 4 is 16. 2 to the power of 5 is 32. All right, so then graphing this function, you end up with something that looks like we have a lot of little decimals there. And then 1, 2, 2, 4, 3, 8, 1, 1, 2. All right, so you have something that looks like this. Now, again, right, because no matter how big the negative number we plug in is going to be, we could plug in -1,000 for x. Your y value is never going to be 0. You can never get a negative number if you're raising something to an exponent. It will only ever give you positive fractions. So because no matter what our x is, no matter how negative we plug in a value for x, it's just going to make our fraction smaller and smaller. We never go below that x-axis. So that's actually going to create another asymptote. There's an invisible barrier that our graph is just not going to cross, and that's going to be at the line y equals 0. This function is called the exponential function. X is an exponent, exponential function. All right, so exponential function. All right, the domain is all real numbers. It goes side to side for forever. All right, you can plug in any x value that you want. So negative infinity, less than x, less than positive infinity. However, your range is never going to dip below the x-axis. It's never going to be negative. So your range is going to be 0 to positive infinity. All right, now it's not 0 less than or equal to y, because you're never actually going to be equal to y. All right, you're going to be less than y. All right, so just know that it's a less than, not less than or equal to. And special features, we have a horizontal asymptote. At the line y equals 0. So we're never going to cross that barrier. Okay, so that is where is my mouse? Hold on, I've just lost it really quick. Oh, I found it. Okay, so those are the notes for today. I hope that was helpful. Use these notes to do the practice problems and to prepare for your target check on Tuesday. All right.